A couple of quick reminders. Today we have from 5 to 6:30 we have office hours in Phillips 428. So my office is in Phillips 428B, but there's a little seminar room next to it, so we can meet there. And I hope people have started working a bit on the assignments and the first assignment. And please, if you have questions, we can discuss them during the office hours today to 6:30 p.m. Right? Okay. And the discussion will not be restricted to the assignment problems, but in general. I mean, any questions you might have about concepts or things we'd like to answer them. Okay. So, and the other announcement is next week, Tuesday, no class. And we are still trying to find a time for the makeup class for next Tuesday. Okay. Right. So. Okay. Let's see what I want to do today is two things. One is complete the discussion on how far can we go by looking at electrons as completely free electrons without considering kind of knowingly and neglecting or being in a denial that there are atoms in the way of the electrons in a solid, right? And we'll see that we can explain a great deal, but then there's way too many things we cannot explain. And then that's when we need to consider that in a semiconductor there are silicon atoms sitting in the path of the electron and such things. But purely subjecting the electrons to the rules of quantum mechanics and not considering the atoms in the way can tell you a lot already, and that's kind of the step-by-step approach we are taking. So historically, Paul Drude introduced the idea of the electron being responsible for electrical and thermal conductivity, but he completely used classical mechanics. And then some of the things that he had predicted, like the heat capacity of electrons, to be something that we derived in class, 3/2 electron density times the Boltzmann constant. This is a completely classical result, and it miserably failed in experimental measurements because nobody could measure it, and it took 25 years since Drude for quantum theory to develop from 1900 to late 1920s and early 1930s, and then Arnold Sommerfeld in Munich at that time, he introduced just one condition, that electrons must follow Fermi Dirac distribution because of Pauli exclusion principle, and the fact that something we have discussed in great detail. And he showed that as a result of that, just the electronic contribution to the heat capacity will become pi square over 2 times the electron density times the Boltzmann constant as it was before. But then there's this big factor sitting in front, which is Boltzmann, or the kinetic kT over this Fermi energy. And this Fermi energy is a purely quantum sort of energy. I mean, even at temperature T is equal to 0, you have that, and that's because of the exclusion principle, right? And we want to kind of complete this story by showing that the free electron theory can explain this very easily, but then explain a host of other things as well. And then we'll see that you run against roadblocks because you're neglecting atoms in the way now, right? And one of the things that the Sommerfeld theory, or quantum theory, you can call it the quantum theory, quantum free electron model of a solid, sometimes called a Sommerfeld theory, and it was developed by both Sommerfeld and Hans Bethe and quite a few people around the same time. So it can explain heat capacity, it can explain thermal conductivity, thermal power, some aspects of transport and all that. But one of the most existential questions is something that it cannot explain, that why are some solids metals and some solid semiconductors, and some insulators. That is an existential question, right? Because we know that they are, right? But this theory will not be able to explain that. It will, and we'll see. For that, we need to consider the fact that there are atoms in the crystal, and the electrons are waves. And now, if you arrange the atoms in a periodic grating, the waves will do what all waves do. They will diffract and interfere, and some electron states will form standing waves they cannot go through. They get stuck because, and that's the origin of the band gap. Right? So we're going to see that, right? So of a material, and then based on the number of electrons, it will be either a metal or an insulator or a semiconductor, and the band gap will be determined by the nature of the atoms, the way, the symmetry in which they're arranged in the crystal. Right? So that's where we're going to go today. All right. So today, what we want to do is, in this process of looking at just the quantum free electron model we cannot call it a semiconductor yet because it is agnostic to what atoms there are in the way. Right? So this is a theory actually for metals, and you cannot. So before the Sommerfeld theory, the quantum, the big question was, how do you explain metallic properties? And after this theory came along, everybody understood metals, and now the question is, how do you explain an insulator? Now, why are some things insulators? Right? So that's sort of the philosophy. Okay, so where were we in the last class? What we were doing was we introduced, and we are trying to learn how to apply, how to think of electron transport in a material in a completely quantum mechanical way. We let go of our classical notions and think of it completely quantum mechanically. And we kind of wrote down a few quantities. First things first, we want to kind of know the wave function of the electron, because that has both the momentum and the k and the x, momentum and the location. And generally, we saw that, for example, in a one-dimensional problem, which we kind of introduced a periodic boundary condition, we put the electron not on a straight line but on a ring, right? And we saw that because of fact that it has waves, it goes around the ring in waves and all that. It must have, if the circumference of the circle is L, its wave function must look like this, right? And k sub n times x, and this is quantized, and so we write psi sub n, right? Those are allowed wave functions of an electron on a ring is 2 pi over L times an integer n, right? So what are we going to do now, just as a overview of what I'm recapping a little bit, but what we realized in the last class is, if we know the wave function, a lot of information is buried inside it, and I can now use it and apply momentum operator, energy operator, current operator, and recover all these quantities, the things that we are interested in, right? And till this point, and I know there was a nice question, there was also an existential question that we haven't, the things that we talk about initially, we are not even introducing two electrons. It's just a single electron is going to have all these features. And the moment we introduce two electrons, we'll be forced to conclude that there must be a Fermi energy, and there's the average energy of the crystal, of electrons in the crystal, and we want to kind of get to that point. And in the process, we are going to introduce today one very important new concept, and that is the density of states. We are going to introduce that when we density of states. It's an extremely important concept in all of condensed matter physics, semiconductor physics, metals, whatever you do. It's a very important concept, and we're going to introduce this concept now. Okay. So the problem we discussed in the last class is the electron is free to kind of move around in this circle, and based on that, you get this is the wave function, and we can apply momentum operator, and we realize that the momentum is quantized, and it looks like h bar times kn, where kn is the allowed wave vectors, right? And I can write this as 2 pi over lambda n, right? K is always 2 pi by lambda. And you can see from here, your lambda n looks like what? L over n, right? L over n, where L is the circumference, right? So, and n can be any integer, positive, negative, 0. If n is 0, that means the electron wave function is pretty much a constant all around. That you can see that, right? If n is 0, the wavelength is infinite effectively, right? It's a very long wavelength. And another way to look at it is k is 0, so you just have wave functions 1 over square root L, right? This is a constant. And then you just have to fit half wavelengths, and when you put n is equal to 1, then there'll be one wave that will fit, and then 2 waves, and so on. Right? So one half wavelength, 2 half wavelengths, and so on. Okay? So those are your momenta. Angular momentum also is basically the radius, which is L over 2 pi times the linear momentum. And we saw that that's actually quantized to, this is pretty much we did the first assignment, a homework problem, one of the first homework problems here. So this is something you're doing now. And we see angular momentum is n times h bar. And that's really also a statement of one of the very nice examples of quantum mechanics, that your particle cannot have any angular momentum. It can only have 0 or 1 h bar or 2 h bar or something like that. So that's a very, very nice example. Then we wrote energy of the electron. You apply the Hamiltonian operator. No potential. Potential is 0 everywhere. And only the kinetic energy term, which is momentum squared by twice mass. And from there, we could write that it's basically this square over twice the mass of the electron times kn squared. And till this point, it need not be an electron. It could be a proton or an atom or whatever be it. It doesn't have to be an electron at all till this point. Till I put 2 of them, and then we're going to ask about the identity of the particle itself. Okay? So what I'm trying to say is, if I had a proton moving around in a circle, the same relations will hold for the proton as well. Right? So, any quantum particle. Okay, so and from this point, we also found actually the current. I'm going to kind of take this as a detour, but first let me finish discussing about the current. So the current, we had written, if you remember, psi star gradient psi minus psi gradient psi star over twice, momentum operator here. We derived this in the class and all that. So when you apply this, take the wave function, apply all that stuff, what you end up getting is for each state, each n here, n is 0, plus minus 1 and all that. Each n defines one state of the one possible state of the electron, right? And so as a result, I can write it as a function of n, or I can write it as a function of k sub n. It's the same thing, effectively. Right? Let me draw a picture of the energy, and then I want to use that to motivate what we're talking about today. So here's the energy dispersion for an electron on a ring. Right? And the things we are talking about right now are, and then things we're going to introduce right now are really the basis of everything else in the future. Density of states, one state. How do you think about 2 states, a mixture of 2 states? So for example, if I take n is equal to 30, let's say randomly, n is equal to 30, right? So where will that state be? Remember, this n is an integer, so in reality, you have these states that are spaced out here, right? With a spacing of how much? The k is actually not continuous, but it's discrete, right? And its spacing is 2 pi by L, right? 2 pi by L, where L is the circumference of the ring, right? That's the spacing. And so if I go and choose, let's say, plus 30 or something like that, and I go up here, and here's that state, right? That n is equal to 30. It's a very well-defined state. It has a very well-defined wavelength, which is L over 30. There are no uncertainties to that, right? So there's no uncertainty. So we can label that state as psi sub 30 or psi sub n, whichever way you look at it, of x. Or even we can think of it in a little more abstract term too. And then this was a Dirac's notation. We can just put it as a vector like that. This is a notation of Dirac. This is just a state n. And we imagine that state this is a little bit of an abstraction, but we'll see towards the end of the class today why it's such a very powerful abstraction, meaning it consumes a lot of the mathematics inside it, and you don't have to worry about those details. So what we are going to think of it is as a vector, in some space, and this is a vector called n. That's a vector called n. It's living in some space. This space is called a Hilbert space. It's irrelevant what's the name and all that. It's just some space. Okay, there's a vector sitting here. I look at 15, that's another vector, state 15, m maybe, and maybe that's another vector here, and so on. Right? So these are all states allowed, and I can kind of individually assign to them a wave function, or I can just write it as a vector. Right? And the way to, kind of Dirac said that this is a better way to think about quantum mechanics. I mean, think of a vector, and if you want the wave function is actually a number. It's a complex number, right? But a vector has a direction and all that too, right? So what he said, how do you get a number from a vector? You take its projection along some axis and you get the length, right? So that's it. So this is the physical way that Dirac said we should think about it that way. What I'm going to project it on is, if I want the wave function in real space, I'm going to project that thing on the real space x-axis, let's say, right? And there's some sort of vector there, and the wave function is actually that length along the real space projection. This is if you're comfortable, good. If not, it's not going to hurt if you don't quite get it. If you want to discuss more, you can come in. But essentially, this is the abstraction we're going to kind of think about. And when I write a notation like this, nx, that means that that's the wave function. I can actually project it in the k space. Maybe there's a k in the k space, which is the wave vector space of the electron. And we'll see later on that becomes also very important if I want to project in k space. And then the wave function will be a function of k. But you can ask, well, is it really different? Because actually the wave function is really that. It already has a k in there. So and all that, right? Okay, so this is, I'll come back to this picture later. Especially when we put in the path of an electron a periodic potential of atoms, this way of thinking becomes kind of important. So, yeah. One of the very nice things you notice right away here is if my wave functions are written, this is my set of wave functions. You can see I have basically a 0 plus 1 state plus 2 state. By just changing the n, right? I get this whole set of functions, different functions. E to the power, for 0, it's just 1 over square root of L, right? And it's kind of starting to oscillate faster and faster as I increase my n, or I go to the negative side, minus 2. Right? So this is a whole set of functions. Or this is a whole set of vectors. If you project it on real space, you get a set of functions. Right? And one of the beautiful things about this is that if I think of it as, let me ask this question. So psi m of x and psi n of x, I take these two, take a complex conjugate and multiply and integrate it over the entire circle, right? What do I get then? So it's very interesting. I mean, essentially you get a 0 unless n and m are equal. Right? Because if n and m are equal, you know that you get 1. That's our normalization, right? But if n and m are not equal, if I take 0 and 1, you get 0. Because they're off rise, and basically one has a different number of periods than the other. And you integrate two different periods over a cycle, you'll always get a 0, right? Does that so and this is essentially what's called the Kronecker delta symbol, nm, but I think physically we know what it means. It's when n and m are equal, it's 1. If n and m are not equal, it's 0. This is the discrete analog of the Dirac delta function. It's a discrete analog, right? Yeah. So I don't want to think of it that way. I want to think of it in an even simpler fashion. I want to go back to Dirac's idea and say that I want to think of these two as vectors. Okay? And when I take the projection of one vector on another, it's giving me the length of that vector along this axis, right? And so what it physically is saying is all these vectors that you have chosen, n, m, if they're different, they're orthogonal to each other. They're perpendicular. These two vectors are perpendicular because when you project something on the other, the length is 0. That's the physical meaning. So these are orthogonal vectors in that Hilbert space. Or in other words, we can just write it as nm is equal to, this is a relation that you can think of. This is orthogonal. And this orthogonality is extremely important because it also helps these two electrons in one state and the other to behave in the crystal pretty much as if there was no other. I mean, they don't talk to each other at all. It kind of makes them independent. This is one of the hearts of why they become, surprisingly, they become independent of each other. They transport, a lot of things are kind of not correlated. In many solids, they're not correlated at all. And this is, okay, so this is the orthogonality condition. I wanted to introduce this notation early on, and then we kind of use it, hopefully, a little more. As we use it, it becomes clearer and all that, okay? Okay, so one of the questions I can ask is, let's say I have not one state, but I have a mixture of two states. I have 90% maybe of, or some percent of, let's call it n, and a little different, maybe 10% of m. And that's also allowed in quantum mechanics. It's no problem. It's completely allowed. Just like, in a state, you think of it here, just in a vector space, I can create any vector with 30% there, and 40% there, right? I decompose this. In the same way, I think of any state you can imagine, which is a linear combination of these two states, an times n plus am times n. That's a perfectly allowed state in quantum mechanics. Right? Perfectly allowed state, and you can ask the questions of whether it's a state of definite momentum. Maybe it's not. Here, it's clearly not, because you can see that this state will have, the electron will behave in a strange way. If you do measurements, maybe 90% of the times you will get a momentum of this much, but 10% of the time you get a momentum of this much. So it's not a state of definite momentum, right? But you can actually find out how many times, if I do a measurement, how much of this momentum is in that state and how much of that momentum is this state. That's related to like mod a squared and all that. Right? So that's the physical meaning of a superposition state, and those states are perfectly allowed. Right? And not only allowed, they're actually extremely useful. But this is essentially a way to look at a combined state. And then I can maybe ask you later on, what is the, if you do a measurement, let's say a state is partly here and partly there, it's superposition state, and you have created it in some way. Then we can ask many of these questions, like what is its energy? Right? What is energy? So in quantum mechanics, the way you answer this question is, well, if I do a measurement of this energy, what I will get is either this or that. I will never get something in the middle. I'll never get it. Right? I'll get either this or that. And the energy of that, if I do that measurement, it'll be either E1 or En or En. That's what it is. Every time I do a single measurement, I get this or that. And that is kind of the hardest part to kind of grasp in quantum mechanics. This either this or that. You cannot have something in the middle. Right? But if I repeat that measurement a billion times or 10 to the 24 times, what I will get is that average energy. If I take a histogram, I get, for 30 times that, 50 times that. So that average energy will be n squared plus am squared times E n. And the coefficient squares always add up to 1. Right. So that's the physical meaning of this. What do we mean by a superposed state? Right? Okay, so I can even ask what is the current maybe carried by a combined state of K1 and K2, and so that will depend on mod n1 an squared times the current carried by that, plus or minus depending upon if that state was here, maybe state P. So that state is actually going the other way. So you can have a current. This is carrying part of the current to the right, and that's carrying part of the current to the left. Right? So I can think of it as individual. You can either think of it as individual, but you can basically what I'm trying to say is you can take your psi and just run through it, and it will give you the total current, right? And so on, right? So you don't have to kind of do any. Once we accept this, what do we mean by the superposition? All these things are, just essentially you can go get those mechanically by applying these relations directly. So what I'm trying to really say is this psi need not be an eigenstate. It need not be pure. So it can be a superposition of many, many states, and that's okay. So you can still apply it and get the current. So that's what physically mean here. And in fact, we'll see when we start talking about real transport in transistors and Schottky diodes in semiconductor devices, we really play with it all the time. Essentially, that's what we are doing. When you apply a voltage, you make some occupation more and some less, and that's how you get currents in these materials. Right? Okay, so let's now look at, in fact, this picture of the current itself. Let's go back to just one particle again to simplify things. One particle going around, and we had derived in the class last time, or you can kind of apply it again, this expression for the current. You just plop that in here, and the current for any state, let's say Kn, will be again, so the momentum will basically kind of pull out the k here, Ik in the front, and you will get 1 over L, where L is that length. Because you have psi and psi star, you get 1 over L. The square root gets squared and all that, and you get h bar Kn over the mass of the electron, right? And all the okay, so this is essentially what you'll get as the flux, current flux. And if we want to add to it, if you want to make it this is the current flux carried by a state n. Is that clear? At least in the flux, which is in classical physics, this current flux is n times v, carrier density times the velocity, right? And we multiply it with the charge to get the electrical current density or things like that, right? In quantum mechanics, that's what it is. And if we look carefully, it is still just like the classical mechanics. Why? Because this quantity here is 1 over L. How many electrons do I have right now? I have only one. I have one electron over a length L, right? So that's the density, one electron in a length L. That is my n, right? And that is the momentum over mass. That's effectively velocity, if you want to think of it. Momentum over mass, that's still the velocity. So quantum mechanics is not telling you something very different from classical, but that's the correlation between the two quantities right there, right? Now one may ask, how is this related to, and then to make it into a current, which I write as a big J, so you multiply it with the electron charge here, right? Because the big J is Q times N times V. That's a classical thing, same thing, right? Multiply by the charge that's dragged by that electron with it. Now what we want to show today is once we consider the many particle picture, we're going to fill it with not just one but many electrons now, and we're going to enforce Pauli exclusion principle and all that stuff. We had seen that this quantity could be written as n q squared tau over mass from Drude sort of relation times the electric field, and this is what we had called the conductivity, right? And we're going to show that quantum mechanics is going to also lead you to the same result if you allow the electrons to scatter and all that now. So we're going to see exactly that same thing again. You can recover. So any new and more powerful theory that can explain more phenomena should also explain all the earlier phenomena and more, right? And then we just want to make sure that's what happens today. Okay, so we're going to see that today. So to go there, the first thing we need to do is introduce, if I had one electron carrying current, that's all, end of story. There's nothing else to do. I mean, the electron is moving like that, and as long as you know it's K, you can find its current density and the current, right? Now, why would the current flow in the first place? That's one of the interesting questions. The current would flow because maybe you have applied an electric field or a voltage, right? You have applied a voltage, and when you apply a force on an electron state, this is a relation I'm going to write down. We are not deriving it in this class, but this is the quantum mechanical. We had written it as a Schrodinger's time-dependent equation, but it's the same deal really. That the force is rate of change of momentum, but momentum in quantum mechanics h bar k, right? So force is rate of change of momentum. That's Newton's law effectively. But here we're writing it as h bar dk dt. And what is this k? That's the wave vector of the electron, 2 pi by wavelength. So if I apply a constant force, and this is an important topic now, if I apply a constant force, meaning force will be electron charge times electric field. Let's say Q is negative here. I mean, that's charge times electric field is equal to h bar dk dt. Electric field is a vector. So if I apply a constant electric field, the K is increasing linearly in time, right? dk by dt is constant, so K is increasing linearly in time. So what is the electric field doing to the electron in the K space? It was sitting right here at the bottom, let's say, right? and then you turn on the electric field, it jumps to the next state here, n is equal to 1, right? N is equal to 2, n is equal to 3, and it's sweeping it up. So the k is increasing, right? As a result, the electron had a very long wavelength initially, and by the time you reach here, it has half wavelength. By the time you reach at 30, its wavelength is shrinking, right? The wavelength is getting shorter and shorter because it's gaining energy, it's gaining momentum. So the wavelength is getting shorter and shorter, right? And the nice thing is the k is being swept out linearly in time. Right? That's a very simple result here, very simple. And that would happen, that will continue as long as you don't let it scatter, right? If you don't let it scatter. Now, let's say you allow it to scatter, and we'll see later, if you let it continue, and by the time it's essentially has way out of equilibrium, and it has a lot of energy to scatter, a lot of chance to scatter, if you can kind of collect it, that's called ballistic transport, no scattering at all. Right? It just goes from one contact to another and no scattering. That is ballistic transport. But we want to kind of relate it to sort of the Drude model where we allow a lot of scattering. So I must modify this relation now, right? If I want to. But I'm now treading on the quantum sort of picture now, right? I'm not doing classical, but this is Newton's law. Remember, we modified it to allow for scattering or damping terms. So oh yeah, yeah. Question.
So I understand how we kept the boundary conditions the same when we went from a linear infinite square well to a circular well. But how come we aren't? Are we just assuming that there are no radiative terms? Like
yes.
Okay.
No radiation, no loss at this point.
Okay.
We'll actually try to answer those questions later, because the thing is, even if I have an electron moving in a circle, it's kind of radiating energy in from electromagnetic theory. But as you know, we can't hold an electron in a circle for free. We have to provide that energy, and that's provided typically by a magnetic field. So you have created a situation such that the electron is moving somehow, or we have physically made a ring, and it's it is being bound by the potential walls of the ring. So, yeah. And in fact, here too, as the electron starts accelerating, it will radiate energy. Electromagnetic energy is, with the cube of acceleration and all that. And perhaps we'll look at it later, but the amount of radiation here is minuscule, absolutely small. It's only when you get up to the kind of close to speed of light that you start getting the copious amount of radiation, which is used in free electron lasers and all that. But or in the chess here, the synchrotron facility. But if you are moving at 1/300 speed of light, that radiation typically is very small. Very small. So yeah, but it's there. Okay. Yeah. Okay. So what we are going to do now is just like we did in classical mechanics, we are going to add our nice damping term, and here's our damping term, right? Tau, scattering rate, and then we again go back and say that if it's scattering, the electron goes out, to accelerated k, and then maybe it reached a certain k, at which point it scattered, and maybe it lost all its momentum and went back to zero again. Right? So we kind of do that sort of scattering cycle. If so, then you can go back and again do the same sort of analysis. And I'm going to lose the vector notation now and write it as dk over dt minus h bar k. But here I think, all right, so I'll just write it like that. And in steady state, again, d by dt's will go away. And from here, you will get the delta k, or in other words, the amount of k momentum it can get before it scatters is steady state is q times tau over h bar times the electric field. There's a minus sign, but I think that's understood. Yeah.
So the k is quantized, but the time is continuous. So
the k is quantized. That's right.
So I'm wondering how that derivative works.
Very good point. Very good point. So you can think of it as infinite differences as well. You can write it as and you can write it as Tm minus Tn. That's fine. Mathematically you can. Right? So and essentially, if you're asking me, is it taking? How does it go from a state that is like that Does it do it discretely? It's kind of it does go through these virtual states in between, when physically, and I don't want to kind of get into that detail at this point, but yeah. Yeah.
So we're assuming dt is 0 because it's bound.
Yeah. So if you remember, the way we reach steady state is you let it scatter many, many times, right? Essentially, what's going is velocity is kind of going up, and then it goes to 0. Velocity going up goes to 0, and you kind of take the steady state. So maybe velocity is doing like that with time, and we have cycled over many times, and essentially saying this is repeating. And I'm going to say what is the average velocity it reaches. So that's what we're doing now. So this is the drift term. And right, okay, so this is essentially what you get, that the electron momentum, on an average would be delta k, because it's not going to be unbound. It's bound by this quantity. Does that make sense? I mean, it doesn't go much beyond that term, right? And as you increase the electric field, obviously this k increases. It samples a little bit more of the k space because of that purpose. Yeah. So I'm going to use that picture, and now what we want to show using the quantum theory, that we're going to recover the classical Drude model of electrical conductivity, but quite a bit more than that. So we're going to just use that picture right now. Any more questions here? We'll come back to this again when we talk about transport in some detail. Right? Okay, so now what I want to do is bring in the question of, or the fact that we actually have more than one electron in any metal, right, or in any nanotube, or whichever way you want to consider. And we are going to now bring that fact in, and I'm going to just clean this up a little bit. All right. And just to be sure I don't mislead you into this, when I draw a line, I mean the discrete states are there. I'm just not drawing it. That's all. They're there. They're quasi-continuous. They're 2 pi by L separated in k space. This is k. This is energy of k, and I can still write k sub n, but I'm not writing it right now. So this separation here is 2 pi over L. Right? In fact, I'll be forced to kind of draw a few points at least right now. But all right, so instead of one electron, now let's go and put in n electrons, right? Big N electrons in the 1D circle. Right? So I put a lot of them. And I had mentioned earlier, if you're looking at a metallic carbon nanotube, we'll be looking at roughly 10 to the power 7 per centimeter of electrons total. Per unit length, 10 to the power 7. Right? That's kind of a metallic density. You can take a pop to the power 3, and then you get a metallic density, 21 or something like that. In fact, let's make it 10 to the power 8 roughly. So in 3D version, it will become 10 to the power 24, right? Cube volume density. So, but in 1D, that's the rough number. So if I know my length, n times or n over L is 10 to the power 8. That's what I mean, right? Per centimeter. That's the total number of electrons. That's the length of the. So I put that many electrons in now. So it's trying to build up to a more realistic situation for a metal, except it's 1D. Right? So now you can see right away, the moment I go from 1 to 2 electrons, already I must ensure that they follow. These are fermions, right? They must follow the Fermi-Dirac distribution, and they must follow the exclusion principle, which leads to the Fermi-Dirac distribution. Right? So exclusion principle means you cannot have two in one state. So essentially, you can have two, but as long as they're two different spins, but that's all. And then you kind of go up, and then you essentially fill up to a certain state. Right? And all this may happen at 0 Kelvin. You don't need any temperature to give that much energy to the electrons. It gets because of the exclusion principle. Right? So now you can say, we are looking at this point completely at phenomena that happens at complete, at ground state or temperature is equal to 0. There's no extra energy. I just have put that much electrons in. I've turned off their charge too, so they don't interact, and all that stuff. But they are fermions. Right? So if there were bosons, on the other hand, if there are photons that I put in there, then they all can be at the bottom state. They don't have to fill up. But because they're fermions, they must fill up here. And immediately, because of that reason, I get two very characteristic quantities. One is what is the maximum wave vector till which you are filled, your electron states are filled, and what is the maximum energy till which you are filled, right? Does that make sense? I mean, immediately you get these two quantities. Just if you give me the number of electrons, I can tell you these two quantities right away, right? And then h bar times that is equal to the Fermi momentum. So this is a Fermi wave vector, Fermi momentum, Fermi energy, right? All three are just determined by the number of particles, number of fermions. Right? And here we must then say what sort of particles there are. Are they fermions? Are they bosons? Because we are beyond. If not, we cannot make any progress, right? So right here is the fork in the road in a certain sense. We have to define that, right? And so maybe you can tell me, how do I find what is kf? That's just a pure counting problem now, right? Pure counting problem. Why? Because I know what is the separation between 2 points here. That's 2 pi by L. And if I have kf here, I'm going to also fill towards the negative direction. The total distance here is going to be 2 times kf, right? And in this window of kf, how many such points are there, you know? Right? So the total number of points then is this divided by 2 pi by L. That's how many discrete points there are. And in each point, how many states can I how many electrons can I put? 2. That's because the spin is 2, right? So I multiply that. So that must be the total number of electrons, and that's all there is to it, right? It's very simple now. You know, if I take that, I should get my total number of electrons right there, right? So I want to kind of rewrite it a little bit because, and you can see whenever I write it in this way, the length, which is the physical dimension, I can take it onto there, and this is what we physically always kind of know what it is. You know, we can measure and all that. Okay, so from here I get like what, 4 by 2 pi and all that. So let's write it down. Kf times 4 over 2, so 2 over pi, right? Is equal to, and this quantity, so it's going to become a bit abusive in notation, but I'm going to still use it as small n, as the carrier density per unit, length or per unit area, per unit volume, and do not confuse it with the integer n, which is also a state. So, but I think it should be clear what it is really, if it has units and all that. This is n, and then I have n here, right? Because I took the L here, the length here, and I get carrier density, right? And from here you get that the Fermi wave vector is equal to n, pi over 2 times n. That's a very simple result, and it's actually correct. So you can calculate it now. I know if I have 10 to the power 8 electrons, pi over 2 times 10 to the power 8 inverse centimeter is the Fermi wave vector. You can also find from here what is the wavelength of that most energetic electron sitting at the highest energy here. That happens to be of the order, let's say, pi over 2 10 to the power 8, right? So again, I mean, just order of magnitude, lambda is roughly 10 to the power minus 8 centimeters. 10 to the power minus 8 centimeters. So that's about an angstrom, right? 1 angstrom, that's the wavelength of the electron. Yeah.
What happens to the L in the denominator of 2 pi?
Yeah, so if I have the L here, that's the total number of electrons. Yeah, so and I take it, so we'll always be dealing with per unit volume because we can make the wire longer or the volume. So we always, so that's where it goes, so the L goes here and I know what's the electron density per unit length here. So, right, so it's saying that, purely because of exclusion principle, if I put in that many electrons, I will have, the topmost highest energy electrons of wavelength 1 angstrom. It's very, very short. It's the distance between 2 atoms. We haven't even talked about atoms, but just if you had that many electrons, you'll have 1 angstrom. You can now calculate the energy. Energy is, h square k square by twice mass. And you can put that thing in, pi over 2n whole squared. You know everything here. If it's electrons, you know the mass, the electron density, plug them in. You will get, I've not done the number, I'm just trying to think, you will get maybe like 15 or 10 electron volts, 10 eV, roughly order of magnitude. You will get that much energy just because of that. maybe a little more. I don't know. You can run the numbers here. Okay, so yeah, you had a question? No, okay. So in maybe sorry, what did I say? Tens? No. It could be in hundreds or even thousands. Depends on how much electrons you have, right? Of EV, very high, very high. Okay. Now, what we is that clear? Any questions here? I mean, you can see that some of these things are kind of you're forced to conclude that this must happen. Yeah.
So where did that extra 2 come from? So you have the 2kF that comes from doubling that, and then you have where did the 2?
Right. So this was a good question. So each state here, this is something we have not discussed. 2 spins. Yeah, up and down spin. In fact, in a real carbon nanotube, there's another 2 here, which is because there is another copy of this in K space somewhere here. So that's called a valleys, many valleys, valley degeneracy. So as long as we know that, so spin will kind of give you a copy of it, so you get 2. If you have valley degeneracy, so typically it's written as valley degeneracy is G sub V, spin degeneracy is G sub S. You put them in, and whatever be a situation, you kind of go with that. Spin degeneracy is 2. If you go and look at a magnetic material in some windows of energy, it has only 1 spin. If you look at a magnetic material, but here spin 2 and valley is 2. Okay, so I'm going to erase this, but we're going to come back to this later. The next thing we do now is ask. These are all consequences of the exclusion principle. Now what we want to ask is, or rather, I'm going to introduce this concept now of the density of states, and the reason for that too. Okay? So the density of states is, in terms of pictures, I'm going to sketch this here. So I have energy, and instead of K, I'm going to write it as G, small g of energy. And I'm going to make a plot in that direction. And that's the density of states. And physically, what it really means is, if I go in and choose a little window of energy here, right? This is energy axis. I choose a little window of energy between, say, E and E plus dE. I choose that window of energy. And in that window, how many states are there? That's the physical. How many states are there? Meaning, I intercept it here, look at the discrete values here, and count how many states are there. That's the density of states, right? So if I take the density of states physically, what does that again would mean? If I take the density of states and I multiply it with that window and I integrate it between any energy 1 and any energy 2, what should I get physically? What does that mean? The density of states would mean I go from E1 to E2, let's say, right? And within that window, how many states are there? It's a number, right? How many states there are, right? So that's the density of states. In fact, if I write it as with a small, notation, small g, that is the density of states per unit length for 1D. For volume, for 3D, it will be per unit volume. For 2D, it will be per unit area. Just like, small n versus big N, same D. Right? But physically, this is actually rather easy to get, because what you can do is, let's say I go from E to E plus dE, and I say that my density of states at that point was big E, which is sorry, not the density. This is the number. Okay. This is the total number. Or rather, okay, so let's put it this way. This is the density of states not per unit volume. Not per unit volume. This is the density of states not per unit volume. And I want to ask that if I go from E to dE, how many states do I have? Right? How many states do I have? That I can also answer from this very simple picture of looking at K space, right? I mean, K space, this energy corresponds to that K. That energy corresponds to that K, right? So you can project it down. So there's a certain dk here, right? And I could equally be counting, instead of along this line, I could be counting along this line. I'm okay, right? Because each of these states has an index here, n is equal to 45, 50, and all that stuff. So I just count along dk. And I write it here as dk. And maybe you can tell me what should it be. So if I know my dk here, then how many states are there within a window dk? That is, you know that already. Because the separation between any 2 points is 2 pi by L, right? So if this length here is dk, then again you get over 2 pi by L, right? And then you have your spin degeneracy again. If you have spin, you have 2, and your valley and all that. So let's not worry about the valley at this point. We just put a 2 here, right? And this is the way you find the density of states. This is the most generic way, and it always works. You're solving an assignment problem with graphene. There you are given the density of states, but I mean, if you were to calculate the density of graphene, this is how you do it. Same deal. It's really nothing fancy. This is it. You're just counting states, saying that if I count 100 states in energy, of course I will also count 100 states in K, because they're indexed. It's the same. I'm counting the same states, right? So left and right. And again, I take this L to the left side, and instead of number of states, I want to know the number per unit area or unit length or unit volume. So that is what the number divided by the length is what we are calling as the small g, or the density of states. That's what I wanted to get, right? Okay. Right. Is that clear? Or any questions here? Because this is a very important concept. I want to kind of make sure that we're all on the same page on this. This is density of states. And what units will I get? I'll get 1 over unit. Remember, this is the density per unit energy, right? I mean, if you integrate it over energy, you get a number per unit length. So it will be 1 over EV per centimeter. That's what it's going to be, because it's density of states in energy per unit length. So that's what you're going to get. That's the units. And then I want to actually write down an expression. I want to make a plot of the density of states here. Right? I don't want to kind of leave it hanging there. And that you can do by realizing that that the density of states, then I can take this k down there, or I can kind of take the dE over here and write it this way. So I cancel the 2's, I get a pi, and I 1 over dE by dk, right? Same thing. And do I know E as a function of k? Of course I do. E is h squared k squared by 2m. I know that, right? So therefore, because the energy is h squared k squared by 2m, and I'm also making some implicit assumptions. You can either think of it, because this k is not continuous as you had asked. You can, if you do a difference function, you get the same deal really. I mean, there's not much even in difference. So that would imply that dE over dk is h squared over mass. I've lost the electron somehow. Okay, yeah, in E. Okay, times k times dk, right? Oh no, what am I doing? D by dk is just that, right? Yeah. So I just get a 2k and all that stuff. And I don't want to write it in terms of k. I want to write it in terms of the energy. And therefore, I do one more substitution, that k is, the square root of me times energy over h squared, right? So just plug that in. 2 mass over h squared. So the mass over h squared will appear again and again in many varieties, and this is one of the first we are seeing. Mass over h squared times square root of energy, right? So that's just d by dk, and I take it here, and I want to write the full density of states. Did I do it right? Yeah. 1 over pi d by dk. That's good. And d by dk is equal to h squared by 2m. Right. Okay. So I want to do a little change. I want to do, I see there's h squared and me. Just multiply by 2. No. What do I do? I want to divide by 2 and multiply by 2. Okay. Just simply massaging it a little bit. And then, so multiply and divide by 2. And you can see now why I did that, because now you get minus half here, right? And that goes away, right? and then I put it here. I want to take it to the numerator. That's the reason I did it. So essentially what I'm going to get is density of states in one dimension. If I do that, all that stuff there is 1 over pi times twice the mass of electron over h bar squared to the power half. It's minus half in the denominator, goes up, times square root of energy in the denominator. It stays in the denominator, square root of energy. Right? Okay. That's how density of states in 1D. Right. In energy, right? Energy. If you are sometimes asked, I mean, this is a trick question. What's the energy? What's the density of state in K space? It is just that, whatever number is sitting in front of K. It's basically, K over, this over 2 pi. Density of states in energy space has this sort of variation. And you can see that because energy and K are related in a certain way. Here it's parabolic. That will set the analytical forms of it. In graphene, it is conical. It's a cone. It's linear. E versus K is linear. It's a cone, yeah. And that's what you're solving in the assignment, right? So let's look at this. This is the density of states. Is it clear what we do? We just are counting electrons. Have nothing, no new physics at all. Just counting electrons and defining a new quantity. Why? Because it's going to become useful soon now. Yeah. So it's the density of states. And you can see physically, looking at the 1D problem at least, if I want to make a plot of this as a function of energy now, it actually blows up at 0 energy. Right? Blows up at 0 energy. So I'm going to plot density of states. That's the energy axis. It's going to start out very big, and then it's going to kind of slow down. Right? That's the density of states. And it's going as 1 over square root of energy. Does that make sense? I mean, so that's the 1 over square root E. And physically, at least, you can see that if I'm out here, geometrically, you can see I have very few states here, right? And I take the same width of energy, and I go down. Here, I have a lot more because these things become flat, right? There are a lot more states. So physically, that's what it means here, right? The density of states here. And in low dimensions, typically, you see such behavior that things will blow up. This is called a Van Hove singularity and all that. Not very important at this point, okay. So that's the density of states, and from here we can write down that what is the number of electrons. We can either kind of start out by saying I know the number of electrons, or say let me just step back. Why is density of states so important? Why am I emphasizing it? Because you can actually measure this directly. We do a STM, take a scanning turning microscope. You can count how many electron states are there as you tunnel electrons in. And the density here will tell you how much electrons can you actually fit in there. So I get a very high current in STM measurement, and I get low and low current. And people have done this for carbon nanotubes. People have taken STM and measured this whole picture. And so this is directly measurable, right? The density of states. Okay, so now if you can see that if I fill up my electrons till a certain point in this density of states, then the total number of electrons is just the area under the curve. Right? I mean, we're kind of going back and forth. We just redefined this, which is the derivative of the area, and now we say, oh, okay, yeah, that's the area. Yes, but because it's experimentally measurable, I want to write the relation again that the total number or the density of electrons is equal to the energy integral of the density of states. And I'm going to do one more thing. I'm going to take it from, you can actually take it from 0 to infinity. You don't have to stop, But something else kicks in, and that is the occupation probability of that state. What is the probability that the state is occupied? The density of states tells you nothing whatsoever about whether that state is occupied or not. It's saying that because of the situation that the electrons find themselves in, they are in a crystal or in a circle or in a metal, these are the allowed states. Now, whether they're filled or not, that's a separate matter, right? A separate matter, and that matter is handled by the Fermi-Dirac distribution function, or the occupation probability, which is, Fermi-Dirac distribution goes to, it's 1 at low energies, and it goes to 0 as you go above the Fermi level. And it's 1 because of Pauli exclusion principle. It cannot be 10. You can't put 10 electrons in one state, right? So that's the Fermi-Dirac distribution. We write it as f of E. And so to find how many electrons are actually there, you must multiply it with the Fermi-Dirac distribution function, right? And that is clearly 1 over 1 plus E to the power energy minus the Fermi energy over Boltzmann constant times temperature. Okay, so So that's and this relation that I just wrote is true in any dimensions, 1, 2, 3, whichever, in 3 dimensions. We kind of talked about the 1D right now, but it's true in all 3 dimensions. That electron density is equal to the integral density times the occupation function, and in 1D it happens to be 1 over length, 10 to the power 8 per centimeter, and 3D it will be 1 over volume and all that, right? So, okay, so I can the reason for defining the densities is actually a little more than just saying how much electrons there are, right? I can now ask, what is the energy stored by all these electrons? Right? What is the average energy? Or rather, remember, we started with, let's get back to this question again. This is the number of electrons, right? Number of electrons. And we want to now ask that if I have this sort of electrons here and I'm going to give the system some energy through whatever means, what is the heat capacity of this electron system now? Right? What is CV? What is that CV of this electron system? And we want to show that it's actually, this is what Arnold Sommerfeld did. He introduced the Fermi-Dirac distribution and introduced this idea and said that I'm going to, here's a new relation for the specific heat for electrons, and that explained and that tells why Drude's model was wrong. That fixed it. So that this is how it works. So if I want to ask what is the net energy of the system, I want to net energy of all the electrons sum up, right? What is the net energy? How do I find that? Right? I just add up all the energies, right? I just add up, I have electrons with this energy plus that energy plus that energy. I just add them all up, right? And that's the total energy. So let's find that. And this is, again, a rather important concept. This is the total energy of the system, of the electronic system. And that is just always just a sum of individual energies. And I can write it E sub k with a k. Same thing. I mean, k is the index here, right? You can write it as a E sub n, m, whatever, I mean, is the index. You have discrete energies, you're just adding them up now, right? The total energy. And so I can also write it as, instead of trying to write it as a sum, I can write it as an integral. I'm going to just integrate it. Why? Because I actually know the expression for E of k. It's just h squared k squared by 2m, right? So I'm going to, instead of summing it, I'm going to integrate it now. Okay. And I'm going to integrate it over k. Actually, you know what? No, I just introduced density of states. I don't want to integrate over k. You could integrate over k. I want to integrate over energy, right? And then you see that if I go to this energy, here's the density of states, right? I have more electrons here than I have there. And all these electrons have an energy of E, which is h squared k squared 2m at that point, right? So what is the energy of that electron in that place? It's E, and how many electrons are there is G of E, right? That's the density of states, right? So that's, then therefore, actually if I were to calculate the total energy, is going to be big G, right? And if I want to calculate what's the energy per unit volume, or unit length of all that, here let's call it 1D, it's unit length, then it will be small g. I think you can see what I'm trying to do here. So this density of states per unit length will be just that. I want to write it as volume because volume is a more general term. In 1D it just happens to be length. So this is the density of, this is the energy per unit volume stored in the electron by the electrons. Does that make sense? Now you can say that what would be kind of an average energy, meaning I know that some electrons have very low energy, some have very high energy. But I want to imagine that if I have 10 to the power 7 electrons, what's the average energy? Each electron had the same energy, what would that energy be? It will be somewhere here, right? Somewhere in the middle. And how do you find the average energy of electrons? Let's call it, if you go back and look at the Drude model, the average energy was 3/2 kT. That was the 3/2 kT, and now it will be very different, right? So average energy would be given by this. Okay, so I'm going to write it as small u, just like we did earlier, and per unit volume u, small uv, because u is generally hard to distinguish between small and big. But this is the energy per unit volume stored in the electron, and then you integrate over all possible energy. You can go from 0 to infinity. Just remember that automatically I mean that it must take into account the Fermi function, because you have to say how much of that is occupied. So the Fermi function is sitting here always, right? Okay, so now we can ask what is the average energy, and the average energy, in some sense I'm going to write it as U V, will be this, the total, kind of the total over the number of particles. I mean, right? You just divide by the number of total energy divided by the number of particles, and therefore this is a relation we'll use rather frequently, and it's the first time we're encountering it in this course at least. So what I'm doing is the average energy by unit volume is the total energy over the number of electrons, or the density you have, right? The total and that is just G of E, F of E. So in a way, if you look at it, what we are taking here are kind of the moments. This is the density of states and Fermi function, and then you multiply by energy. And let's say later on I ask you, what is the average velocity of all the electrons here? Then the quantity energy, instead of here, you would have the velocity of that electron. What is the average spin of electrons, right? You put the spin of that electron and all that, right? So that's what we mean by this quantity. We're taking an average, over the entire distribution. And the energy, you can take it from 0 to infinity, really, 0 to infinity. Physically, it will be cut off by bands and Fermi energies and all that stuff. But this is kind of a rather important parameter here. Right? So electron density per unit volume, we define in terms of the density of states, and we also get the energy in terms of the density of states. Okay, and now I'm going to calculate what is this answer for the average energy for a 1D system, and then I'll also calculate for 2D, and for 3D you're doing it in your homework. So I'll not do that. Okay, is that clear what we did? We define a density of states, and we're saying from the density, I would rather think about the density of states. From there I can get my electron density, I can get my energy, I can get pretty much all other parameters I'm interested in. And I'm asking in 1D, what is the average energy of electron, of fermions that with a density of electron density of n. So what is the average energy? So how do I find that? Well, I just plug in, right? I mean, all that you need to do here is you have an expression for energy. In fact, you don't need, you have an expression for density of states, just plug it in here. Done. There's nothing else to do. And the only complication is at non-zero temperatures, you have a Fermi function that kind of does that. Fermi function kind of. I'm going to ask you an even simpler question. Let's do it at 0 Kelvin. At 0 Kelvin, what happens to the Fermi function? It goes up and it drops abruptly to 0 at what we're calling as maybe the chemical potential or the Fermi energy at this point. So it is an abrupt function, right? So your integral could be running from 0 to infinity, but you can see that this function just is a unit step that stops at EF, right? Doesn't go any further than that, right? So all we need to do then is it's actually a rather simple integral from 0 to EF, and you have dE times E times the density of states. And the density of states has a block of stuff, a bunch of stuff sitting in the front, but I'm interested in this quantity mostly. I mean, obviously I'm interested in the others too, but I'm interested in this quantity primarily because it's an energy integral, right? So what I'm saying is there's a bunch of stuff here times 1 over square root of energy times the Fermi function, but that's actually 1 between 0 and EF, so not writing it. Is that clear? That is the numerator. Denominator is the electron density n, and I rewrite that, and now I write just the dE times no more energy. Right? This is the density of electrons, the same bunch of terms times same 1 over square root of energy here, right? And that bunch of terms cancels out, right? And don't need to, this constant, right? Just cancels out. And from here, you can see that you get a square root of energy in the numerator. When you integrate square root of energy, you get EF 3/2 divided by 3/2, right? It's a simple integral, right? 0 Kelvin, remember, this is 0 Kelvin approximation. And in the denominator, you get this, so you get EF half, right? Fermi energy half over half, right? Is that clear? Right? Yeah.
Why are we not
Oh, yeah, no, we did in the sense of because we are at 0 Kelvin, the Fermi function is, yeah, right. So, it is 0, sorry, it's 1 and then it goes to 0. So I cut it off. But if you are at a finite temperature, it will change. Right? It will change. And to answer the heat capacity problem, you must consider temperature. But I'm not doing it just to kind of make sure that we, anyway, so here, what you get is, the halves and twos or cancel, you get 1/3 of the Fermi energy. Right? And indeed, I mean, it's somewhere between EF and 0, and the average is saying is 1/3. Does it make sense? Yes, it does make sense because I have a lot more bunching of electrons here at lower energies. Right? Density of states is higher here, so it's weighted a bit towards the lower part of it. Right? That makes sense. It's 1/3 of Fermi energy is. Now, if you add in the effect of temperature, what we'll see is this quantity will physically what will happen if I give heat to it, right? If I give heat to this system, and I give an energy kT to it, so a window of energies kT can kind of absorb that energy and go up here. But the rest of it are completely dead because they're Pauli excluded. If these electrons, if they absorb energy kT, they're not going anywhere because that state is occupied, right? It cannot go, right? So there's a little window. So this kT over this entire EF, that's the fraction of electrons effectively that will get kind of respond to heat, right? And that's really what also appears here in the heat capacity kT over EF. Okay, so now, so is that clear, by the way? I mean, so we get that. And now I want to just do this quick for the 2 dimensions. Let me just think, did I complete all things? So the density of states, the way it's calculated, and the role it plays in the finding the energies of a system. So that's what we talked about. And maybe I'll summarize the 2-dimensional case in the next, part of next few minutes. We have like probably 5 minutes or so left. So let's finish that up. So in 2 dimensions, essentially instead of just one k-axis, now you have 2 axes, one kx and one ky. The electron is free to move in 2 dimensions now. So I can think instead of instead of a line, now you are in a square. Let's say it could be a rectangle. I'm not restricting it to a square. And now we are looking at it from the top, and the electron is, free to move anywhere along the xy axis, right? And now in 2 dimensions, we are going to actually again. You can introduce hard wall boundary conditions and say that the electron is not going to get out of this. The V is infinite here. You can do that. That's called the hard wall boundary condition. But we want to do a periodic boundary condition. And a periodic boundary condition in 2D is actually very interesting. You can take this sheet and you roll this, connect it to that point, right? Right. So what do you get then? It's a cylinder now, right? Yeah. And then that's right. And you get a circle, and then you close it, you get a torus, right? It's a interesting topological object now. So you get like a torus. Oh, sorry, it's the wrong way. Yeah. Something like that, right? It's not clearly not to scale, but you get a torus, and now essentially when the electron is moving, let's say in some direction here, you're kind of going this way or you're going this way. Depends, right? And so it's just a mathematical construct to make sure that my wave function will be periodic, right? And just to be clear, we are not going to lose any physics by doing that. It's a mathematical construct because you can do hard wall boundary condition and you will kind of get the same results in the end. It's no different. Yeah. But we're going to do that. But maybe you can tell me, I don't want to kind of go through all the derivation. How do I write my wave function now, right? What should be a good starting point? It's a free electron. There are no atoms in this 2D electron gas. It's a free electron, no potential. So what should be the trial wave function to start with, right? Yeah, so right, we must go and look at e to the power I k dot r sort of picture, right? Again, and in fact, let me just finish off this normalization. In 1D, what was it? 1 over square root of length, right? Here, it will be 1 over square root of area, right? The total area here. So let's write that down. Total area, e to the power I. And this will be essentially, you can think of it as kxx plus ky times y. There are 2 k's, kx and ky. So it can have basically a wavelength along this direction or a wavelength along that direction, or it can have just a state along this or just that. So that is essentially your k dot r, right? You can write k is kx times a unit vector along the x-axis of k space times ky y, and r is x times unit vector y times unit vector, right? And dot product of this is what gives you this quantity, right? So that's a trial wave function, and it actually works. I mean, so that's how you can say. So from here, what is the momentum of the particle? If I have, or rather, before I go to the momentum, what are the allowed values of kx and what are the allowed values of ky, right? We want to see that right away. And that's, again, determined by the length. If you know Lx and Ly, right? You get a 2 pi over Lx times, you'll have two integers now, n sub x, one quantum in number or integer, the other 2 pi over Ly times n sub y, right? And let's assume for simplicity that Lx and Ly are same, it's a square, it's not a rectangle. Let's assume that. I mean, if it is necessary to assume otherwise, you can go back and change it. But it won't change most of the physics we're talking about at this point. And based on these, I would write it not as kx, but maybe kx with nx or something like that. I mean, just remember there's an index here. Again, just like for 1D, there was an index. There's also an index here. So in other words, the k is really a vector which looks like 2 pi over L times nx comma ny. Does that make sense? It's really a vector, right? It's the electron wave vector. What is the momentum? You can check it, apply the momentum operator in 2 dimensions will be the gradient, and that means it will be x plus y d over dy. This is the operator. You apply it on this wave function. If it's a momentum eigenstate, it will give you the momentum. And what the momentum you will get, you will see that this is indeed a momentum eigenstate. For free electron, the e to the power I theta is always an eigenfunction for momentum and energy. So what you will get here is the momentum is a vector, as it should be in 2 dimensions, and its quantity in a magnitude is h to L, and the vector is pointing along k vector. Is very straightforward, just h bar times that k. That's the momentum. And finally, I think we are done with time. The energy of the is again h square k square by 2m. So you can do h square by twice the mass of the electron. Again, you have k 2 pi by L whole squared. But now you have nx and ny. Mod square of that is nx squared plus ny squared, right? So that's your energy. These are all the allowed energies. And when you plot it, you instead of a parabola, you get a paraboloid. And basically, you rotate this around k squared. That's very simple, right? It's not complicated. In the next class, not on Tuesday, but on Thursday, what we'll see is we are going to again apply all these things, ask what is the density of states now for 2D? And we'll see it will not be 1 over square root of energy. It will be a constant. And that's a very important result. We'll see the density of states by using this EK diagram. You can evaluate it by yourself, right? It will be a constant. You'll see that. It doesn't depend on energy. Then you go to 3 dimensions. You have another Z, right? And the density of states in 3 dimensions would go from 1 over square root of energy to just square root of energy is going to increase. So that's how the dependence of dimension the dimensionality of electrons of the problem has a huge effect on heat capacity, on density of states and all these things. So we kind of see that. Okay, good. So let's finish for today, and we'll have office hours from 5 to 6:30 today. Okay? All right. Thanks.